Hello, this is Dr. Joe Trout at the physics program at Stockton University. And today's we're going to talk about rotational motion, and we'll do a review of momentum. So if you remember, momentum is defined as the mass times the velocity. So it can be written as a vector, and it's the mass times the magnitude of the velocity at an angle, or the mass times the velocity in the x direction times I plus the mass times the y component of the velocity times j plus the mass times the z component of the velocity times k. We also talked about something called impulse. An impulse was equal to the integral of the force with respect to time. And we found that it was equal to the change in the momentum. So the net force we found is equal to the time rate change of momentum. So let's consider a hard object bouncing against a hard surface. In this case, it could be a gas molecule hitting the wall of a container or a cylinder. So in this case, only it's a really large gas molecule. So in this case, we have a 2-kilogram mass moving at 5 meters per second, making an angle of 60 degrees with respect to the horizontal. And it's in contact with the wall for 0.202 seconds. And it repels after it collides with the wall with a velocity with a magnitude of 5 meters per second. So it looks like kinetic energy is conserved, and this is an elastic collision. So in this case, if we look at the change in momentum in the x direction, right, it looks like the mass doesn't change and the component of the x velocity doesn't change. So it looks like the change in momentum is 0 in the x direction, and therefore the force is equal to 0 in the x direction. However, if we look at the y direction, we get 2 kilograms, right, times the velocity, which is 5 meters per second times the sine of 60 degrees, right, minus a negative 5 meters per second times the sine of 60 degrees. In this case, we end up with 8.66 kilogram meters per second. If we want to look at the y component of the force, it's the change in momentum in the y direction divided by the change of time, or 8.66 divided by 0.02, which equals 433 newtons. We're going to need this in a couple of chapters when we try to define what pressure is. Let's say we have a force that acts and for 10 seconds, so it starts at t equals 10 seconds and ends at t equals 20 seconds. And let's say the force is linearly increasing with time. And we're going to look for the area under this graph. So what we end up with is the area of the triangle. That's 1/2. 10 newtons minus 5 newtons is the height, and 20 seconds minus 10 seconds is the width. And then add in the area of this bottom rectangle, which is 5 newtons times 20 seconds minus 10 seconds, and we end up with 75 kilogram meters per second. You might notice that this is the same units as momentum, and the impulse in this case is equal to the change in momentum. This problem is a modification to the ballistic pendulum we did in class. So here, a 5-kilogram rifle fires a 2-gram bullet, and the bullet is fired into a 1-kilogram wooden block, and it rides up a frictionless curve. And the bullet embeds itself in the ramp, in the block, and it travels up the ramp to a height of 0.12 meters, so 1.2 centimeters. And we want to know what the initial speed of the bullet is, as it leaves the rifle barrel, and what is the speed of the rifle as it recoils. So what happens? It embeds itself, and we want to know what the velocity is when it embeds itself, and there's no friction, so if the velocity is constant along that horizontal surface, and then it reaches some maximum height and comes to a stop. So for the second part of the experiment, we find that the change in kinetic energy is equal to the change in potential energy. So down here we have kinetic energy. That's 1/2 the mass of the bullet plus the mass of the block times the velocity squared. And it moves up the ramp and it loses kinetic energy and gains potential energy. And finally, it ends up at a height of 0.12 meters. And our potential energy there is the mass of the bullet plus the mass of the block times GH. So our velocity after the collision is equal to the square root of 2 times 9.8 times the height, 0.12 meters, or 0.48 meters per second. So this is the velocity after the collision. So as the collision takes place, we can use conservation of momentum. So we have the mass of the bullet, the velocity of the bullet, that's the initial momentum, is equal to the mass of the block plus the mass of the bullet times the velocity after the collision. We already know what the velocity after the collision is. It's 0.48 meters per second. So now we can solve for the velocity of the bullet. All we have to do is divide by the mass of the bullet. So we get the mass of the block plus the mass of the bullet. That's 0.002 kilograms plus 1 kilogram divided by the mass of the bullet, 0.002 kilograms, times the velocity after the collision, which is 0.48, and we end up with 248 meters per second. So this is just like the ballistic pendulum we did in class, only we used a frictionless curved ramp in this case. How about the recoil of the rifle? So we want to know what the velocity of the gun. Let's say we just let we just hold the trigger and then hold on to the gun, or this would be the velocity that you feel that you have to absorb in your shoulder or whatever, wherever you're holding the gun. So we find out that initially the momentum was 0, that the block and the gun were sitting still. Then after the explosion of the gunpowder inside the cell casing, we end up with momentum of the gun, which is the mass of the gun times the velocity of the gun, plus the mass of the bullet, the velocity of the bullet. And we can solve for the velocity of the gun. So the velocity of the gun will be equal to minus the mass of the bullet over the mass of the gun times the velocity of the bullet. So you get 0.02 kilograms, the mass of the bullet, divided by the mass of the gun, 5 kilograms, times 240.48 meters per second. Sorry, I forgot to put the meters per second in here, which comes out to be about a slow speed, about 0.096 meters per second. We also talked about perfectly elastic collisions, right? And we have these equations. So in this case, if I look at this mass, M1 is 5 kilograms and M2 is 50 kilograms. And we're going to fire M1 into M2 and it's going to collide elastically. That means that the momentum's conserved and the kinetic energy is conserved. And we have these equations that we found in class. So in this case, our velocity of 2 is 0 initially. So our final velocity for 1 is the mass of 1, 5, minus the mass of 2, 50. So that's negative 45 over 55 times 10. And we end up with negative 8.81 meters per second. So that was minus 45 divided by 50 times 10. And I'm sorry, minus 45 divided by 55 times 10, which is 8.18 meters per second. And it's going off in the negative direction. And then 2 moves forward a little bit. So what we get is the velocity at 2 initially is 0. So we get twice m1, that's 10, divided by 55. So that's 10 divided by 55. And then times 5, that times 10, and we end up with 1.82 meters per second. So the mass comes in, it hits the first velocity, but the second mass, and it bounces back, and the second mass moves forward. If the second mass was moving, we would find out that the second mass moves forward with about 3.43 meters per second, and the first mass moves backwards. Okay, so now we have a puck on an air hockey table. And at first we can tell the hot puck is moving pretty fast because there's big differences between, and these are snapshots taken at every 10th of a second. So what we want to do is figure out there's obviously a particle here that we don't see that leaves off in this direction. So let's see if we could figure out what that would be. So first, let's figure out what the initial momentum is. So there is no initial y velocity momentum because we're moving just in the x direction. And if we look at the x momentum, it's the mass times the velocity. And it looks like it's constant. So let's see, we get 0.09 because these are measurements are in centimeters. So 0.09 meters minus 0.03 meters divided by the time, and there's 2 pictures here, so that's 2/10 of a second. And we end up with 156 kilogram meters per second. So now we'll find the velocity of the puck we see and find out what the momentum is. And from there, we can figure out what puck is missing. So we'll go ahead and figure out what the x velocity is. So for this case, we have about 20, or I'm sorry, 0.19. Sorry, these circles are a little bit off. We're going to use this dot and this dot, right? So we start out at 19 and we go down to minus 15 centimeters. And there's 1, 2, 3, 4 pictures taken. So it's 4 times 9. And then if we look in the y direction, it's 5 minus 1, right? And we can figure out what that velocity is. So that means that the x velocity of that second puck, or the x momentum of the second puck, must be 0.01 kilogram meters per second. And we can also figure out what the y components are. So we'll find out what the initial and the final components are for the puck that we see. And then we can figure out what the final momentum is for the puck we don't see. So we can figure out what that final momentum is, and we can figure out what the final angle is. So we know that, and if there, and let's say that the puck that we don't see is 0.52 kilograms, we see that that puck that we don't see must be moving off with a speed of 0.287 meters per second at an angle of minus 52 degrees. Also, as a review, we talked about space flight, right? And we're looking at a rocket and it shoots out gas out the back, and we can think of it as tiny particles moving at a high velocity. So if we look at the momentum of the ejected fuel, it's equal to minus dm times the velocity of the fuel, but the velocity of the fuel is the velocity of the rocket minus the velocity of the exhaust. So what we end up with is a momentum initial has to be equal to the momentum final. And this is our initial momentum. It's the rocket times its velocity. And then this is the momentum of the rocket after it loses some mass and moves forward a little bit. And this is the momentum of the gas particles being shot out the back. So we do some algebra and we realize that dm dv must be really small. And we see that the thrust is equal to m times dv dt, which is minus v exhaust over dm dt. But the acceleration is dv dt, so we can integrate both sides over dt, and we end up with the integral of dv minus the exhaust velocity times the integral of dm over m, starting with an initial mass and ending with a final mass m. The integral of 1 over x is ln of x, so the integral of 1 over m is ln of m, and we evaluate it at m and m naught. So we get the natural log of m minus the natural log of m naught, but that can be written as m over m naught. If we switch the order and make the numerator the denominator and the denominator the numerator, it would reverse that negative sign. So our final value is that our velocity equals our initial velocity plus the exhaust velocity times the natural log of our initial mass over our final mass. Okay, so let's talk a little bit about rotational motion. Here we have a circle. And how do you get a circle? You take a radius, all the points that are equal distant from some center point, right? And we'll call that the radius r. We could look at the arc length, and we know that the arc length is equal to r theta. So theta is equal to the arc length over r, and the arc length is the length of that dotted line. If you'd like, you could call the arc length equal to L, and theta becomes L over R. So we want to make theta as small as possible, but this is a good approximation. Don't forget, we have 360 degrees in a circle. So we go 0, 90, 180, 270, and 360. And for radians, we have 2 pi radians per circle. So it starts at 0, goes to pi over 2, pi, 3/2 pi radians, and up to 2 pi radians. So we see that 360 degrees is equal to 2 pi radians. So for instance, if we have 30 degrees and we want to convert it to radians, we'll multiply it by 2 pi radians and divide by 360, and we get pi over 2 radians. If we want to convert radians back into degrees, we have 4/5 pi radians, and we'll multiply it by 360 and divide by 2 pi, and we end up with 144 degrees. So let's say we have a circle and it rotates. And now we have some angular position. So it hasn't translated at all. It hasn't moved up or down or left or right or in or out of the page. But what it did was rotate. So now it has a new angular position. And we'll call this angular position delta theta, or the change in the angular position as delta theta. Just like our change, if we're moving in a line, is delta x. So we can define something called the angular velocity. This is a lowercase letter omega, and it's equal to d theta dt, just like our velocity is equal to dx dt. The units are a little crazy. So really, the unit should be radians per second. But if you think about it, radian isn't really a unit. So normally we just write the unit as 1/seconds. Don't forget, the angle is really a ratio of two distances, so it's unitless. We also have angular acceleration. So in linear motion, when we translate, we called that dv dt. So this time it's going to be d omega dt. And the symbol we're going to use is a lowercase alpha. That's like the letter A. So it's a lowercase Greek letter alpha. So the angular acceleration alpha is equal to the time rate change of omega, and it's equal to d squared. And it's equal to the second derivative of theta with respect to t. Now we're going to make a bunch of analogies. Before we had x, now we have theta. Before we had velocity average, now we have omega average, which is theta final minus theta initial over t final minus t initial. Before we had an acceleration, which was delta v over delta t. Now we have angular acceleration, which is delta omega over delta t. And we have velocity, dx dt, and angular velocity, omega equals d theta dt. We have acceleration, dv dt. This is instantaneous acceleration, and instantaneous angular acceleration, d omega dt. So we're not going to rederive all the equations again because the math is exactly the same. It's just that the symbols have changed. So before we had, for instance, acceleration equaled 0. That was our first special case. If acceleration equals 0, the velocity was constant, and we could predict our position. Now, if angular acceleration is 0, then omega is constant, and we can predict our angular position. So it's theta equals theta naught plus omega t. So let's say we have a disk and it rotates at a constant rate of 5 revolutions per minute. How much does it rotate in 2 seconds? So we have 5 revolutions per minute, but we need to convert that to radians per second. There's 2 pi radians in every revolution. So there's 2 pi radians in every revolution. So the revolutions will cancel. And 1 minute is 60 degrees, so the minutes cancel. So we end up with pi over 6 radians per second. Then theta is equal to omega t. This is just like a delta x equals velocity times time if the velocity is constant. So we get pi over 6 radians per second times 2 is pi over 3 radians. If acceleration is constant, in the translational case, we found that velocity was linear. velocity was equal to v naught plus at. And we could predict our position. X was equal to x naught plus v naught t plus 1/2 at squared. And we had this extra equation for finding the velocity as a function of position. So we had velocity squared equals velocity initial squared plus 2a delta x. So now we just switch all the symbols. For a, we put alpha. For v, we put omega. And for x, we put theta. And we come up with the exact same equations with just different symbols. But all the math is the same. So for example, let's say we had a disk that was rotating at a rate of 20 radians per second. And it was accelerating at -2 radians per second squared. So how long before the disk comes to rest? All right, so our angular velocity is equal to our initial angular velocity plus alpha t. And we can solve for t. So our final velocity is 0. Our initial velocity is 20. And our acceleration was -2 radians per second squared. So it took 10 seconds for this to slow down to a stop. This is just like the problem with the car moving forward and accelerating quickly to a stop. Only instead of the car moving forward, this circle is rotating. So how many radians before it comes to rest? It's equal to theta equals theta naught times t plus 1/2 alpha t squared. So we end up with about 100 radians, right? Which is about 15.9 revolutions. Sorry, this should say revolutions right here. Okay, so we want to talk about something called tangential velocity. So let's say this woman stands still on a disk that's rotating. And she moves this distance, right? So really, we could define a velocity, which is just the distance s, the blue line, divided by the time it took. So we have s equals r theta. So ds dt, which is the velocity you're moving along this blue line, would be equal to r, which is constant, times d theta dt, or r omega. And if we look for the tangential acceleration, we'll just take the time derivative of that. But the time derivative of omega is d omega dt, which is just the acceleration. So for example, let's look at these two people. And they're standing still, but the disk rotates. So what we see is that the person that's closer to the center is moving slower, even though they're both rotating at the same rate. So if we look at person 1, right, they move a distance of 25 meters, and their velocity is 2.5 meters per second. And if we look for the velocity and the distance that 1 went, then we end up with 5 meters times 0.05 radians per second, the same velocity, but we find out that the person is moving at 2.5 meters per second. I'm sorry, this is the same one for us for T1. So if we look for 2, what we end up with is that, I'm sorry, if we look for 1, we end up with 10 meters times 0.5 is 5 meters. and the velocity is 5 meters times 0.25, or we find out, or 10 meters times 5 is 5 meters per second, and we see that our distance would be 5 meters per second times 10 seconds, or 50 meters. All right, so we have this idea of a tangential velocity. That's the distance divided by the time, and it's equal to r omega. So you know what? Now we can talk about a rotational kinetic energy. So in this case, we have 1/2 the mass times the velocity tangential squared. But we know that that velocity tangential is just r times omega. So in this case, we're going to replace the symbol mr squared with the letter I and call it the moment of inertia. Okay, and that's where we'll pick it up on Friday.